This video is the fourth in the series of tutorials discussing the LX7720 radiation-hardened motor drivers for space. In case you haven't seen the other videos, here's a reminder of what the LX7720 actually is. The LX7720 is a mixed-signal peripheral, which works with an FPGA or a microcontroller to build a complete closed-loop brushless DC motor controller or stepper motor system. The first two videos outlined the LX7720 at a system level, and then dived into a detailed discussion of the half-bridge drivers. The previous video introduced the LX7720's 4 current sense amplifiers, which were intended to measure motor winding currents. This video will discuss the 3 common current measurement topologies used with motors, and will show how to connect a current sense amplifier in each topology. There are 3 alternative ways to set up current measurement with a half-bridge: ground side sensing, motor supply side sensing, and motor drive output sensing. The difference between the 3 topologies is not just the position of the current sense resistor, but also how the current sense amplifiers, the CSPS supply rail, and the return ground are connected. In all 3 cases, the current sense amplifier's CSPS supply rail is either directly connected to or derived from the VGS gate drive supply. Now, let's go into the detail for ground side current sensing. Here's a complete half-bridge stage with current measurement in the source leg of the lower NFET. The red arrows show the current flow into the load when the upper NFET is on, and from the load to ground when the lower FET is on. The current sense amplifier is powered from VGS, decoupled with an RC filter. The current sense resistor develops a positive voltage proportional to sink current when the lower NFET is on. When the lower NFET is turned off, commutation current, sunk from inductive load, will ramp down through the upper NFET's body diode into the VMPS, as shown in blue. Current flows sourced through the upper NFET into the load won't be measured. If the upper and lower NFETs on times overlap, however, the shoot-through current will be detected because it will pass through the current sense resistor. Also, when the upper NFET is turned off, commutation current to the inductive motor winding will ramp down through the lower NFET's body diode, as shown in green. The current sense resistor will develop a negative voltage proportional to commutation current. The sense voltage range is bipolar, plus and minus 250 millivolts, so this reverse current flow will be measured. Next, here's a complete half-bridge with current measurement in the drain leg of the upper NFET. Again, the red arrows show the current flow into the load when the upper NFET is on, and from the load when the lower NFET is on. The current sense amplifier is powered between V-boost and VMPS. V-boost is a super voltage sitting at about VGS volts above the VMPS power supply. The current sense resistor will develop a negative voltage proportional to source current when the upper NFET is on. When the upper NFET is turned off, commutation current sunk from inductive load or ramped down through the lower NFET's body diode into the VMPS power supply, as shown in green. Current flows sourced through the lower NFET into the load won't be measured. Again, if the upper and lower NFETs on times overlap, the shoot-through current will be detected because it will pass through the current sense resistor. Also, when the lower NFET is turned off, commutation current to an inductive load will ramp down through the upper NFET's body diode, as shown in blue. The current sense resistor will develop a positive voltage proportional to commutation current. Lastly, here's a complete half-bridge with current measurement in the drive output. The current sense amplifier is now powered by the upper drivers of the VFLT floating supply. VFLT floats relative to the SW pin, so the current sense amplifier's supply and inverting input RTN is therefore connected to the SW pin. The current sense resistor will develop a negative voltage proportional to current sourced from the half-bridge, and the positive voltage proportional to current sunk by the half-bridge.